Hello community! Today we're gonna have fun because we're gonna talk about Super GPT system. And you have a question. You ask me, hey, can I ever understand here the AI research from UC Berkeley even if I'm not a theoretical physicist? Yes, of course, come on! Look, this is the latest publication, UC Berkeley, 22nd of March 2024. And it is about LLM2LLM. So let's have a look at this. And this is only for my green grasshoppers. Everything is green here. So LLM2LLM, data augmentation, fine-tuning, low data regime, synthetic dataset generation, and dataset augmentation. And here we have a little bit more complicated, but this is old days, LLM2LLM. You have two large language models communicating with each other, and there's no human interface. AI to AI. Isn't this beautiful? Come on! Let's have a look at what is the research from UC Berkeley on this. If you have a problem, simply find a different mental representation of this information. Let me show you my simplest way I can think about this. Here we have a pre-trained LLM and we have a domain-specific dataset for this pre-trained LLM. And you know exactly what we do. It runs for weeks and months, and then given here the precise data information, we have a pre-trained LLM, and the same happens if we have a domain-specific dataset for the fine-tuning of our LLM. We have the fine-tuning, and then doing the fine-tuning, we arrived at a fine-tuned machine. But imagine if we have not enough training data. Our domain-specific dataset for the fine-tuning is too small, maybe just 1 or 2 data points. This is a problem, and this is where AI machines help other AI machines to generate missing data. So if we only have A1 and A2, 2 answers, and the rest is missing, you know exactly what we're going to do. Because if we now fine-tune here our LLM and evaluate it, we see the answers A1 and A2 are there, but A3 to A10 is missing because we are not having any fine-tuning training data for this. So what do we do? Well, we ask here, this is our little student LLM that we want to teach the new trick, and we have to have here a beautiful, beautiful super GPT system, GPT-5, GPT-X, whatever you like, and we use this extremely trained on the internet GPT system to identify domain-specific topics. Topics that are within the domain, but where the answers A3 to A10 are missing. So we identify the topics and we generate within those missing topics of our domain knowledge. The Super GPT system generates there the training data set for the specific configuration of our little fine-tuned LLM, our student LLM. You see, it is rather simple. So our Super GPT generates new domain-specific data for very specific topics that it evaluates that the system has not fine-tuned data yet, and it generates this training data. Beautiful, can be done easily, and then we fine-tune it, we evaluate this fine-tuned system, and we see A3 and A4 are here, and the knowledge has been generated, has been fine-tuned. Now we have domain-specific knowledge added to this with our synthetic new data sets that Super GPT generated. And you might ask, hey, why not extract pieces here of this LLM weight tensor structure? Just extract them here for a student model. Why we have to go over data structure and do the fine-tuning methodology? Well, more about this in a later video, but this is a really interesting question. We might come back a little bit later. So here we go and say, okay, we generated training data, and if we have the training data generated, then it is perfect, and we have our fine-tuned student LLM, our little fine-tuned LLM for a domain-specific downstream task. Isn't this great? Okay, so this is it. Those scientific paper, LLM2LLM, does a fine-tuning of a student LLM on an initial data set where we just have answer 1 or 2, evaluates this training data set, extract data points which the model got incorrect after the fine-tuning, and we use a self-instruct style data augmentation to augment these data points here that are missing, and we add here those data points back in the training fine-tuning data set. I mean, GPT-4 Turbo does this for us, so we have an LLM teaching another LLM by providing here data. They refer to the self-instruct publication here by University of Washington, Johns Hopkins University, and Allen Institute for AI. And in this publication here, you see the latest version from May 2023. They go here with aligning language model with self-generated instruction. But however, be careful about the performance. Look, here we have 4 different teacher models. And you see the Llama 2 70B model achieves only an accuracy below 20% with this LLM2LLM methodology. Below 20% is not really something that we should be saying, wow. And even if you use as a teacher LLM GPT-4 Turbo and we pay for all of this, we just achieve below 30%. So there's nothing famous about this methodology. But if you have no other training data points, at least if you have this super GPT system, you can generate synthetic data for this little LLM to learn here. And this is the important point of this publication. Now, I know that you want to know here a little bit of prompt engineering, so let's see what UC Berkeley did with system prompt. This is the original system prompt from UC Berkeley for an AI agent, and they said, hey, you are a question GPT. You are an AI agent who knows here the class of a different question, and let's go and generate here a synthetic data set for our little student LLM. You see, this is the original prompt that they used, and you see, if you read this, you understand it immediately. Yes, of course, it is a human-induced large language model. Beautiful. Now, if you take this and I put this into my GPT-4 system, and you want to see the outcome, and here it is, we just generate question in a particular classes in a particular topic that is currently missing in the knowledge pool of our LLM. Here, another system prompt for an AI agent who is now a transcript GPT system to identify that what people intents are when they say something, what is their original intent. This is the original system prompt here, and you see if I put it in my ChatGPT-4, this is exactly the training data that are generated. So you see, it's easy. However, we should critically assess this with respect to the quality of the synthetic data, the transferability of the learned representation, and in particular about the specific alignment of the synthetic data with the domain-specific characteristics of our system, let's say theoretical physics. So, 8 points. First, the quality of the synthetic data. If the teacher model lacks here a comprehensive coverage of the domain-specific knowledge or it exhibits biases, we have a problem. And the complexity and the diversity of the real-world data distribution is not mapped from teacher to student. Or, second, transferability of the learned representation. If we have assumptions that do not hold, particularly for domains that are substantially distinct from the data the model was originally trained on, this representational discrepancy can limit the effectiveness of our synthetic generated data, as the nuances here of the domain-specific data fail. The alignment of domain-specific characteristics. The synthetic data must encapsulate here the idiosyncratic features of the domain-specific data. We have some jargon, we have some specific phrases we use. All of this must be in the training data. And a divergence from these can lead to a synthetic data set that, while it's big and huge, it fails to provide here the nuanced signal necessary for the student LLM to achieve a high performance here in the specialized task that we train it for. Fourth point, Dependence on seed data quality. You remember we have here some seed data. They heavily depend the system on the quality of the seed data. If it contains inaccuracy, is too narrow in scope, or is not representative for the broader domain-specific challenges. All the iterative processes by generating synthetic data may amplify those shortcomings. And this is something we do not want at all, because we want our synthetic data to cover the whole spectrum. Point number 5, the model capacity for reasoning and for creativity. This is so important to simulate causal reasoning and creativity within this particular domain impacts the quality of the fine-tuning process. The model must be adapted, creating synthetic data points that not only reflect the complexity of the domain problems, but also present them in different contexts that encourage here some robust learning in our student LLM system. So you see, not so complicated at all. Point 6, the risk of data leakage and overfitting. Of course, always. A risk that the teacher model may not replicate the pattern in the correct way. Think about the computational resources you need, the temporal resources you need that might incur during this LLM2LLM process. It's quite expensive, especially if you go with a higher structured causal reasoning chain. And of course, we have ethical and social consideration, because those synthetic data must be evaluated in terms of the ethical and social implications, especially if we apply those models here to sensitive domains, like, for example, medicine or health treatment. So wherever there's a bias or wherever there's something in our data, we have to be very careful with synthetic data generation. And we have, as humans, to make sure that all the data that are generated by the machine are used in a responsible and ethical and social acceptable way. There's no way around this. Okay, so you see 8 points where synthetic data generation, even at the beginning here of April of 2024, there are so many problems we have to tackle here in our AI to AI communication. And I just wanted to give you this. Even if you have an easy looking publication, the depth of the problems that you can encounter with those LLM to LLM model can be significant. But I think this is it for today. I hope, my little green grasshoppers, you enjoyed it. You see the different representations are there. Just choose your way how you want to approach this data, and all the information and all the research is done that we have here, the AI system that could augment here human knowledge, make us faster, make us better, improve our conditions. And therefore, do not be afraid if you see some complex scientific literature. It is easy to understand. Take your time. I'm sure you will succeed. It would be great to see you in my next video.